2, arc length and surface area. So the questions that we're going to be looking at in this section are basically, well, let's say we have some curve. That's the graph of a function, y is equal to f of x. That maybe looks like this. How long is this curve? If we walk along this curve, how far do we walk? And so realize that, if this is just a straight line, it's a very easy calculation to do. But if this is a very, very curvy curve, well, how are we going to go about calculating it? And a similar question that we'll look at later in the section is surface area of a solid of revolution. So back in section 6.3 and 6.4, of course, we would take some curve, we'd take the area under that curve and revolve it around some axis, and we would find the volume of that solid of revolution. Well, in this section, we're going to do the similar setup, take some curve, rotate it around, but instead of calculating out the volume inside there, we're going to look at the surface area. Just how big is the surface area? And so instead of having like a 3D calculation like volume here, it's going to be a 2D calculation for area. Okay, so let's get into thinking about how to tackle this question, the arc length question. So let's get some axes going on here. Here is our function f of x. And the question is, how do we approximate this? And so one way that we can do this is that we can approximate this with straight line segments. So we can just kind of take different dots here. And so then here's one dot on the function, 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 and just connect them up. And so we'd be able to, for each one of these, we'd be able to calculate out the length because those are straight lines. So maybe this gives us a decent approximation. And then we're going to be kind of taking the limit as these dots get closer and closer together. And this should start feeling very, very Riemann sum-ish. And so that's basically what's going on. Well, let's start off by thinking about a straight line segment here. Maybe this one right here. And we want to ask ourselves, how long is it? And let's say that the length is ds. So ds is our length of the segment. And then let's see what else. We can form a right triangle here, and we'll call this dx and dy. So dx is the horizontal length, and dy is the vertical length. And so let's think about Pythagorean theorem. What does it tell us here? It tells us, the Pythagorean theorem tells us that ds squared, I'll put parentheses to indicate really that ds is a single quantity. So ds squared is equal to dx squared plus dy squared. Okay, let's take the square root of both sides. So ds is the square root of dx squared plus dy squared. And now let's divide under the square root. Let's divide both of these by dx squared and move out a factor of dx outside our square root. So what does that give us? That gives us, so dx squared divided by dx squared is 1. dy over dx, so we basically can think about this as a kind of informal derivation, but that should look familiar. dy over dx squared, the slope of the tangent line squared. So what's going on here? ds, our little chunk of our line segment, is equal to the square root of 1 plus dy over dx squared dx. Okay, so how do we go from here? Total arc length. How do we, so let me recopy this. We want to sum up, quote unquote, sum up all of these little chunks of length. But how do we do sums here? Well, we're going to sum up all of these as the chunks get smaller and smaller and smaller. And so there's going to be more and more of them. There's basically, we're taking a limit as the chunks get smaller and smaller, as we get, as the number of them goes off to infinity here. So what we basically end up with is we're integrating. So S is the integral of ds, is the integral from a to b, the endpoints. So in this picture, this would be from a to b, of the square root of 1 plus dy over dx, quantity squared, dx. And so all of this is going to use to give us our big formula for arc length. So assume that f prime exists, and it's continuous on the interval from a to b. And the arc length s of y is equal to f of x over the interval from a to b is, s is the integral from a to b of the square root of 1 plus f prime of x, quantity squared dx. So here I'm writing f prime of x instead of dy dx, equivalent notations. This is our big formula. So we'll be using this quite a bit in the future. It's also worth noting that if we have, instead of, so in the previous slide, it was assumed that we're writing f as a f of x, y as a function of x. If we're thinking of x is a function of y, then a similar derivation would give us, I'll skip the details, but you end up with the integral from c to d of dx over dy squared plus 1 dy. So same formula here, where you're just integrating with respect to x instead of, you're integrating with respect to x up here. Down here you have x as a function of y, so you integrate with respect to y.